Good morning, everyone. Good afternoon if you are in different time zone. Today, my name is Stefano Cadarvi, and today I'm going to talk about managing inter-processor communication with heterogeneous devices. And together with me, we have Anders Rosvall from Embedded Artist, who's going to talk more about the hardware setup for heterogeneous devices. So without further ado, let's start with the webinar. So today I'm going to talk about the heterogeneous devices in general. So what are the advantages and why we have heterogeneous devices? Then I'm going to go a bit in depth about the inter-processor communication, which is the main topic of this webinar. We're going to look at the hardware setup I have here, and then we're going to give a brief demo of how you can debug and do inter-processor communication. And at the end, we're going to have a summary and some time for question and answers. So from an ARM perspective, we have three main architectures. When we talk about ARM architecture, we actually mean more than one single architecture. There are different types of architecture. So we go from the Cortex-A type architectures. Those are optimized for high performance and for rich operating systems. Cortex-A processor normally have an MMU and normally run complex operating systems such as Linux. The Cortex-R architectures is designed for high performance, but at the same time with keeping in mind the hard real-time applications. You can find this kind of processor normally in hard drive or in the industrial or in automotive, and they normally have a very fast response or fast interrupt response. Last but not least, we have Cortex-M processors. Cortex-M processors are the smallest and the lowest power of the three, and they are optimized for microcontrollers. So if you have a microcontroller, normally you have a Cortex-M processor in it. So we can find these kind of devices in the IoT, for example, in armband and watches, or intelligent light bulb and small devices like that. So if we talk about the different requirements needed when we look at processing power, if we take a mobile phone, for example, when we use the mobile phone, most of the time is in standby. So the processing power needed for staying standby is really low, because the mobile phone is just to wait basically for a call or for a message to notify the user. When we are using the phone to surf or to play some games like Angry Birds, the processing power required is much higher. So as you can see, we have different kind of requirements in terms of performance and power consumption, which we always need to keep in mind, because we don't want the mobile phone to consume the same power when it's on standby, and then comparing to one we are playing Angry Birds, for example, on our mobile phone. Same thing we can talk for a watch. So most of the times it just needs to show the time and keep the time, but maybe when receiving a call, if it's a smartwatch, we might need to use some streaming audio to the watch or video, so the processing power required is much higher. So heterogeneous devices have been created with that in mind. What we have in heterogeneous devices is a Cortex-A processor, so a high-performance processor able to run a feature-rich OS such as Linux and complex application. We can also build complex or advanced user interface with a Cortex-M processor, which is normally used for microcontrollers. Cortex-M processor have very low I/O latency. They have very low power comparing to the Cortex-A, and they're very fast to start up, because we don't have the kind of burden of a Linux kernel need to boot up. Normally, on the Cortex-M processor, you will run an RTOS. It could be RTX, it could be FreeRTOS. It really depends on what you need. An important bit of heterogeneous devices is how we do inter-processor communication. So how we communicate between the Linux application and the RTOS application, and we're gonna go into more depth later on during this webinar. In terms of use cases for heterogeneous devices, we can see in industrial, for example, consumer or medical devices, which are very common in the industry. We normally have the Cortex-A managing the user interface or the high computational tasks, and the Cortex-M managing the real-time part of the device or the low-power part of the device. So if we can take, for example, a medical devices or a heart rate monitor in a hospital, we might want the device to monitor the heart rate of the patient continuously. So we need to be sure that the heart rate is at the right level, and we need to make sure that this is monitored, because we might want to call the doctor or send a signal when something is not really right. But the user interface needed is the user interface might be off. We might not need any specific high performance out of that. When the doctor comes around and he wants to see the historical heart rate of the patient, in that case, we might need to fire up the user interface. And the user interface might look at a database for the historical data, might do some complex analysis on the data. And in that case, the Cortex-A is actually the ideal processor to do this processing. In terms of software challenges, what are the complications? Because we have two completely different or separated operating systems running on the same device. So one of the challenges is task partitioning. So which means how do we allocate different tasks on different processor. So for example, I want the monitor of the heart rate to be on the Cortex-M rather than on the Cortex-A, or the other way around. The second issue is data sharing. How do we make sure that data between the Cortex-A application and the Cortex-M application are synchronized and coherent? How do we make sure that the messages are going from one side to the other correctly? And last but not least is developer productivity. As I mentioned earlier, because we have two different operating systems running at the same time, this creates a more complex debug environment, because we will need to monitor two different operating systems at the same time, and potentially we will need to look at how these two operating systems are interacting together. So in terms of software challenges when developing software, we have, as I mentioned multiple times now, running multiple operating systems on the same device with just one connection, really one debug connection. And so we need to debug bare metal code on the Cortex-M side. We normally have an RTOS, so FreeRTOS or RTX running on the M4. At the same time, we need to look at the Linux application, which we might need to debug with a GDB server. On top of that, if we have problem with communication, for example, we want to debug the Linux kernel, we might need to debug the Linux kernel as well. Last but not least is the communication between the two devices. So it's not really debugging one application or the other application. We might actually need to understand how the interaction between the two works. In terms of communication, one option that we have is to write the communication stack by yourself. This is normally not really advised because it can be quite complicated. So the only way the two application or the two processor can communicate is by using a shared memory and interrupts. So on the Linux application, on the Linux side, we will need to create a kernel module to be able to access directly to the area of memory that is shared with the RTOS. We will need to take care of the segmentation and the managing concurrency of access to data, read and write, and we need to use the kernel mode, of course, for the kernel module. In terms of bare metal, so on the Cortex M4 side, we will need, again, to manage concurrency. We will need to manage the integration with RTOS, with interrupts and so on, and directly handle the memory management. As I said that at the beginning, this is not really what we advise. What we have available instead is a standard and called OpenMP. OpenMP is a set of libraries which allows a simplified way to communicate from the Linux application to the RTOS application and the other way around. It provides an RP message module, so a kernel module which can be loaded in your Linux stack, in your Linux kernel, and it provides an easy interface from a user space, an easy interface to communicate with the other side of the unit. On the MCU side, we have a library, a C library, which can be used to communicate with the Linux application, again, without really big effort. And we're going to see that next. So one of the problems that we might have when communicating or sharing memory as well as peripherals within two processors and two separate operating systems is the how can we make sure the one processor is not accessing two resources that are allocated to the second processor. So the IMX devices have a very nice mechanism called resource domain controller. The resource domain controller is basically a gate which or gatekeeper that allows different processor to access to peripherals and memory, but it will check that each unit or each domain, as it is called, can have read access or write access to that specific memory. So if we see, for example, in this case, we have an example of a UART2, which is allocated only to the M4. In this case, we can set up the RDC to make sure, the resource domain controller, to make sure that only the M4 is able to access and read and write to the UART, to the peripherals we defined. If the Cortex-A7 is trying to read or write from that peripherals, the processor will block this access and error will show up. In terms of interprocessor communication, as I said, with RP message module, with the RP message module which is part of the OpenMP, we in the Linux side there's a TTY created. It's called normally /dev in /dev, of course, TTY RP message, and it's possible to simply read and write as it was a normal TTY. So with the simple IO, even with the echo, we can see later, we can write messages directly to the other application. These messages pass through a virtual pipe in the shared memory, and the message is then picked up from the libraries in the so the library calls in the MCU application, so in the Cortex M4, and the other way around. So if there's a write request on the RTOS side, the message would magically appear on the device that the RP message is created. So this means that from the Linux side, we don't need to write any kind of module. We don't need to have any special access or kernel application. We can just use the TTY as it was a normal TTY. It's effectively a virtual TTY. The mechanism used for the virtual TTY is called virtual.io, and virtual.io has been created, originally developed for a KVM, which is for hypervisor, basically Linux-based hypervisor, but it's been reused for this case. It's been adapted specifically for OpenMP, for communicating between the two processors on heterogeneous devices. So I won't go into details with that, but basically virtual.io will create a virtual queue, and it will use a buffer called vring to manage the different messages that are sent or received between the two systems. And the IMX devices provide an what we call interprocessor interrupts. So whenever a message, one of the two processors send a message to the other processor, there's an interrupt happening on the receiver processor to make sure that the message is handled. In terms of how we can do the communication and the actual function calls that we will need to do. Is relatively easy, as you can see from this graph. On the Cortex A7, we just need to load the Linux module. We can write a message directly with a pipe. We can write directly to TTY RP message, and the message would appear immediately on the Cortex M4 side. We need to initialize the pipe first, of course, from the M4 side, but then we can just use simple functions such as receive, no copy. In this case, we will need to copy the buffer. We have different choices how we can do the communication. So we can have a no copy send or receive, where the memory is pretty much the message is not copied in memory. To avoid any overhead, or we can just have let's say simpler functions where you will when you receive a message, the buffer is allocated on your side, and you don't need to copy specifically that area of memory. One of the questions that we usually get asked about inter-processor communication and RP message is the performance. What's the performance? How fast can I push messages from one side to the other? We did some tests. So what we've done, our test case is from the MCU application, so a normal Cortex M4 RTOS application. We sent a message with a specific size. The Linux application was listening to this message, and as soon as you receive the message, you will reply with the same message, basically, back to the MCU application. And we measure the time between the send of the message from the MCU application to when it received. So it's basically a round trip time. We measure the round trip time from one side to the other. What we found is that using the standard components, so without doing any performance improvements, any hack or any specific adjustment, we found that we could get about a megabyte of bandwidth, megabyte a second of bandwidth on one side. So it would be, so if you're talking about the round trip time, you're talking about half of that bandwidth. And in terms of setup time, so the time necessary for basically the overhead of the channel to create the message and send the message, is about 50 microseconds. So as you can see, we have a good rate of bandwidth to communicate or for messaging, and a good reaction time from one side to the other. Of course, this data can be improved. So in this case, for example, if you want to, in this case, we used small packets, a series of packets, but if you need to move lots of data, you can just allocate data in memory and making sure that the Linux application or the MCU application is just reading from the area of data, because the memory is shared. There's no effective transfer between one and the other side. There's no transfer involved. So now I'm going to hand over to Anders, who's going to talk about the hardware setup.
Yes, thank you very much. For those of you unfamiliar with embedded artists, let me just give a quick introduction. We provide ARM-based computer on module solutions based on NXP technology. We have a family of pin-compatible boards that we call EA-COM boards. We have a strong industrial focus, and we offer at least 10 years longevity. We are also a proven partner to NXP, meaning that we have a lot of knowledge of their products and have a proven track record also with their products. We provide high quality technical support directly from our engineers. And I also want to mention that our slogan is the art of embedded systems development made easy. And that means that we want to lower the thresholds when working with embedded systems. Okay, can you please move on to the next slide, Stefano? Thank you very much. We have IMX Developer Kits for all our COM boards. They are flexible hardware platforms together with documentation and guides. And you see here also a screenshot of our current list of documents and guides. And we have a lot more in preparation also. As I said before, our kits are supported with high quality support. And this is to get you up and running quickly for prototyping and building proof of concepts. Can we move on to the next slide, please? Thank you. So, a little bit more details about the demo board used today. It is our i.MX Dual Developers Kit. The i.MX Dual is a 1 GHz dual-core Cortex-A7 processor core, and it also has a 2 MHz Cortex-M4 core. The board also has 1 GB of DDR3L RAM and 4 GB of eMMC flash. And there is also 1 gigabit Ethernet interface. So all in all, it's a quite powerful platform to start your heterogeneous multiprocessing adventures on. So that was it from Embedded Artists. So over to you, Stefano.
Thank you very much, Anders. So in terms of development environment, what I have actually here on my desk is the Embedded Artists IMX7D Developer Kit. Plus we have our DStream SD debugger connected to it. So we have the obviously debugger, the JTAG debugger connected to the JTAG 10 port on the board, on the Embedded Artists board. We obviously have connected the power and UART as well. So we connected UART to our to my basically computer to USB port, and we connected Ethernet as well, so that we can connect with GDB server as well. The DStream is connected currently with USB, but we have an Ethernet port as well, so potentially you can connect the DStream having on the server farm, for example, or a debug farm, a continuous integration farm. What DSMDK can do, so DSMDK, which is the development suite that we're gonna use now, is able to connect via the JTAG connection, so to do the hardware debug on the Cortex-M4 or the Linux kernel to the A7, or we can use the TCP/IP connection to debug Linux user space applications using TCP/IP, as I said, using GDB server. So effectively, we can have all the view of the device with 3 different channels of communication. So JTAG on a Cortex-M, JTAG on a Cortex-A for the Linux kernel, and TCP/IP to connect to Linux applications user space via GDB server. Okay, so without further ado, I'm gonna switch to our DSMDK. I'm gonna put it here. That should be visible now. So DSMDK is based on Eclipse, and it uses the DS5 debugger for the debug engine. So it's a very powerful debugger. It's a multi-core, multi-processor debugger, and it's very powerful tool, and this is very especially useful when we do heterogeneous devices. So one of the things that we introduced is the ability to use CMSIS packs. So CMSIS packs are the standard for ARM devices to basically have support into development tools. For the DSMDK, we support the various series of IMX 6 and 7. So we have the IMX Dual, for example, what we said now, but we could also access by really search for the board. In this case, we have the IMX 7 Dual, and we can see the device which is mounted on. So the packs are a way to extend support for new devices. So which means that if, let's say today, DSMDK doesn't support a specific device, we can add later in time a new device by just releasing a new CMSIS packs. In terms of packs, we have various, obviously, support for libraries and third-party libraries as well, but also we have examples. Examples are really, really useful because are tailored to the specific board, which means that you don't need to spend time going download the SDK and trying to figure out how to build it. You have your example already integrated in the pack, and you just, with literally one click, you can copy that in your environment. So as you can see, this is the normal Eclipse environment with CDT, so that you have C and C++ syntax highlight and everything. Obviously, DSMDK includes the ARM compiler, so the high performance ARM compiler 5 and uncompiler 6, which is normally it's normally, it performs normally better than other maybe free compilers, and has basically supports all the ARM processors. So it's developed internally within ARM. So this is the application that an example that I already created. We can build the project. In this case, I think is already built, but we can just clean and just build it. Here we go. So in this case, we are using uncompiler 5. The example is built for that. And what it's doing is compiling basically every single file. It compiles, in this case, it's compiling also the libraries. So you can see on the right-hand side, we got OpenMP, because it's effectively building the OpenMP libraries from scratch, so that we enjoy the best optimization level. Here we go. Take a while because it's a bit a big project. Yeah, oh, okay, it's finished. I was about to show you something else. So at the end of the build, we can see the ROM size and the memory size used by the project. So now that we build the project, we can debug it. So what we're going to do, we're going to debug as CMSIS debugger. So the configuration is relatively easy. We just have a DStream here in this case. So we just browse the DSMDK shows up that it's connected to USB, so we can use that. In this case, the image which is loaded is the one we just built. This is the default behavior, so you won't need to change that. And one other things that is very important and useful is to add OS awareness. OS awareness is a way for the debugger to understand what operating system is running on the device, which gives you more information on tasks and mutexes and thread, and it's really useful when you're doing debugging of your project. We support a various set of OSs, but this can be extended as well. So it's possible to write plugins to extend it to your specific example. Okay, so before starting the debug, I wanted to make sure that we have the connection with the Linux system. So here we go. Yes, so in this case, Linux, we can reboot. Here we go. We can reboot the device. As you can see, I'm reading, I'm using the terminal tab, which allows me to connect to the UART directly, so that I don't need to use any different tool to look at the messages coming from the serial port from the Linux side. So everything can happen in the same window. As I said earlier, DSMDK is designed from scratch to be multiprocessor. So when we do the connection, we want to make sure that the user or the developer can have access to everything he or she needs just in the window. So in this case, I know that the login is just root. We might need to do the configuration of the Ethernet. That's correct. So we don't have IP address. So we're gonna set it up so that we can connect as well. Here we go. So in this case, I just assigned the IP address to the Linux system, and I'm gonna try to ping my computer. Let's say if it works. Yes. So that means that my computer is visible from the Linux system running on the board. This allows me to actually create, oh, this is already created, so that's brilliant. I can create it from scratch, it's better. Create from scratch, here we go. So DSMDK has the remote system view. The remote system view allows you to connect directly to the Linux system via GDB or SSH. We assign this IP address, so we just connect it. And one of the benefit of doing this is, the password is always the same, is the ability to debug your project Linux application via GDB server. So for example, the project that we just copied earlier, we can build it. Here we go, it's built. You can see how to debug it and debug configurations. Let's see how we can debug it. Linux application TTY, that's the application where we are talking about. As you can see, we identified the RSC connection, so the connection that we created a minute ago. And when we do debug, basically the system will just connect via GDB server, and this allows us to connect the user space application on Linux. This is a very simple application that writes on the TTY RP message. We haven't actually created the TTY RP message, so that's why we're gonna see the error. Okay, so the next step is to load the kernel module that we talking about. So modprobe IMX RP message TTY. So this is the kernel module. Let's create it. At this point, the channel hasn't been created just yet because, say, if we try to list it, we won't find TTY RP message. This is because the kernel module is waiting for the application, for the Cortex-M4 application to start so that it can connect and create the channel between the two. So what we're gonna do is, now that we built the project, I'm gonna show you from this side because it's more clear. We're gonna just start the debug. So let's go right click, debug as, CMSys DS5 debugger, and this is all set up. We're gonna debug it. Finger crossed this works. It's a live demo. Here we go. Yeah, great. Here we go. So what happened now? The debugger, so the DSMDK, connected to the D stream, which is connected to the M4, and it downloaded the image in memory. So the image that we just built is loaded in memory, and the first thing is stopped is hardware init, so just the first instruction of main. One interesting bit is that now the terminal seems frozen, and it's interesting because I had this problem when I was preparing the demo and I couldn't figure out why. And we found out actually this was due to the resource domain controller. So at this point in time, we haven't set up the resource domain controller for to reserve the Linux, so the UART that we're using for Linux. And so when the M4 is stopped, it automatically stops the UART 1. So whenever we reach this point, when we reach this this point, we're gonna see that this is now enabled. Actually, I can just do the next step. And what happened? Now the TTY is free because we set up the resource domain controller in the correct way. So we now stop to RP message RTOS init. So the M4 is just about to create the channel, to initialize the channel. So, and if we continue with that, the channel has been created. So we can see from the M4 side that the channel has been created. And as well, on the Linux side, we can see that the driver is created. So if we now try to look at the TTY RP message, we can see this is now available, okay? The M4 is still running, so we have both running. But when we stop, we can see that this is stopping in the true. So we don't know what is actually waiting for, what the M4 application is waiting for. And one very useful functionality that the DSMDK has is the RTOS awareness. So as you can see here, we can see the RTOS has different tasks actually running at the same time. So how can we find out where per each task where it stopped? Where's the last instructions has been executed. So one functionality we can enable is display threads. So what happens, we got a different view here. So I can see the active threads and all threads into my M4 application running. And what we are really interesting is about where this is stopped. Again, the TTY thread, which is the one that is handling the communication between the communication between the two systems, it's stopped at these instructions, which doesn't really help me a lot. So what we need to do is go into stack, and we got a call stack. So the call stack here refers exactly to the thread which is shown here. So we can select each thread, and the call stack will change. So let's go to TTY thread. And let's see where is actually stopped. Here we go. So we can see from here that the TTY thread is stopped at RP message RTOS received no copy. So the application is now waiting for a message to be received. So what we can do now is, first of all, continue to run the application, because we want to see, we want the application to be able to handle the message, and we can write a message. So echo my message is that easy to communicate with the other side. Here we go. So as we can see, what happened on the M4 side, we have get message from us side. So that means this is showing that the message is gone through one side. So the Linux application, we just piped the information into TTY RP message, and it appeared on the other side exactly as we expected. Here we go. So in summary, the heterogeneous devices have a very good advantages. So we have a Linux, a feature-rich Linux, or a complex operating system running on the Cortex-A side, as well as an RTOS, real-time RTOS running on the MCU on the Cortex-M side. We can see how we simplify the way we do inter-processor communication using RP message. The RP message are part of CMSIS pack, so it's even easier to integrate that in your application. And you can see that DSMDK supports multi-core debug as well, so we can connect at the same time. Sorry, to the device. Here we go. So if you are interested in using your using DSMDK, you can download a trial. You can get a 30-day trial from www.cal.com, and if you look for DSMDK, you can find the form where you can ask your evaluation.
In case you want to start your HMP adventures, as I said before, you can, for example, order an IMX Developer Kits from our website. And I also want to push a little bit more. I mean, now we have seen Stefano working with DS-MDK, which is really an excellent tool for this kind of development. It gives you very good support. I must say. We use DSMDK all the time in our internal development at Embedded Artists. But what I want to push also for is that we have 2 upcoming workshops where you can get hands-on experience yourself. And we have one in just 2 weeks' time in September 28th in Eindhoven in the Netherlands. We do that together with our distributor, Logic, in the Netherlands, that you can have a look at. There is a link there. And then also there is an Embedded Conference Scandinavia that is in November 8th in Stockholm, Kista. There are 2.5 hour slots, one in the morning and one in the afternoon, where you can get hands-on experience with this particular developer's kit, and you get training on DSMDK also.